All right, well, I tried to do the live script. It worked okay, but the plots weren't showing up great. They were still showing up as separate figures. Sometimes they were on the side, sometimes they weren't. I think it was going to make things more confusing. So what I'm probably going to do, I also realized that you wouldn't have been able to see the plots. So luckily I figured that out. Otherwise, we would have done like 55 minutes of this shenanigans and you wouldn't have been able to see anything I'm talking about. You see me like moving the mouse around, but it doesn't even show you the plots that are showing up on my screen. But I think what I can do is I can share the screen differently. So I can share each individual figure and sort of bounce back and forth. Hopefully it doesn't like give you motion sickness, but I think that's probably the best way to do it. All right, let me clear all, close all, and CLC again. And we're going to just start from scratch, but we're going to go quickly. So let's go first to the MATLAB. All right, where's my MATLAB? There we go. All right, so now you can see the screen. And hopefully I zoomed in a little more so you can see that a little bit better. All right, so we cleared all, close all. So here we are. We're in the right folder. We're going to do the UI get file. We're going to load it all the same. I'm going to pick the same file, which was GF walking loaded, Team 99. You can see all that stuff imported from Vicon. I'm going to clear, accept anything we need right here. I'm going to pull out the subject number right here. You can see it pops up down here in the bottom command window. Make this a little bigger so you can see what's happening down there. Okay. And now I was saying before, I wanted to actually like plot what it looked like so you can see just how noisy it is because we're going to filter it. And the reason we're filtering it is because there's just noise in the data and it's high frequency noise. So let's see if we can see what that looks like. So I'm going to make a new figure here and then I'm going to plot, and I want to plot some of the analog data. So what I'm going to plot is, again, you can't remember the name of it per se, you can go to analog data, right? And here again, if we looked at the labels was FX, FY, FZ. Let's plot FZ, right? So that's the third one. So analog data. This is the one I'd want to plot. So there it is, analog data, curly bracket 1, 3. So now I go back to my editor and I say, I want to plot analog data, curly bracket 1, 3. So if I make a new figure and plot it just like that, it pops up. You can't see it, unfortunately. But now if I go to stop sharing, start sharing, maybe if I just share screen 1, that'll be the way to do it instead of individual figures. Right, so then now you can see this figure. So this is what it plotted, right? So on the y-axis, it looks like we have force. This looks like sample, right? So this goes 6,000 samples over our 5 seconds. And this should look familiar to you, right? This should be like you have 0 force for a while, and then there's this sort of double hump. 0 force, double hump. So we opened up a walking file, right? We knew that to start with, but even if I didn't tell you, this looks like a walking file, except it's flipped, right? It looks inverted because if you think about it, this is what the treadmill is feeling and what the treadmill is measuring, not what the force on the person is, right? From Newton's third law, those are going to be flipped. So this is your force on the treadmill, and in turn, the treadmill is applying this same equal and opposite force to you on the opposite side. All right, so let me stop sharing this again. And maybe if I go and just share my whole screen 1, that'll make it better. So now I think you can see everything that's on this screen, including these figures that are going to pop up. Okay. Hopefully it's not too big so you can actually read some of these, the details of some, but I'll try and make them big when needed so you can sort of see what the forces look like. Okay. So also, if we wanted to zoom in here, the whole reason I did this, right, is if we wanted to sort of zoom, see stuff like this, right? So what's going on here? This is really just noise in the data, right? So you can see it's like really quickly changing up back and forth. This isn't the actual force that's acting on them. This is just sort of high frequency noise from how we collect it from the sensor data. So we want to kind of get rid of this. It's not as big of a deal. You don't notice it as much, right, in the vertical direction because there's such a huge amount of force going on. So the noise is kind of small. But let's say we go here. I'm going to plot the second one. So this should be anterior and posterior direction. So if I plot that now, right, this noise starts to be a little bit more significant. You can see there's like this spike when we're getting heel strike, there's a spike, right? There seems to be a lot of fuzziness going on up here, right? So if you're trying to find what's the peak force in the posterior direction, right? Like, I don't know, well, am I going to take this point right there? Really, the actual force is probably a little bit smoother from what we've seen. Like, and what's happening at this point here, is that really the force changing that quickly, or is that just noise? So we're going to do a little bit of filtering and cleaning up of the data. So what we're actually going to use is, it's called a Butterworth filter. So the way MATLAB does it is you need the sampling frequency, the order of the filter, the cutoff frequency. So this is going to cut off any force that's above 35 hertz. So if the force, if this, right, is changing in direction, basically, this is kind of a simple way to say it, but if it's like changing in direction more than 35 times a second, right? So the things that are really happening quickly, it's going to filter that out. And it's basically going to remove it. It's going to smooth what this looks like. So again, this isn't a data sort of filtering class. So we're just I'm going to apply those Butterworth filters. I'm going to name the 19th analog label now button, because we know that's the button. And then this is a loop. So it's going to go from 1 to 19. So it's going to go through every single one of our analog data cells. It's going to apply this filter, and then it's going to basically create a new variable that's called basically whatever the name was on analog labels. So I'm going to run this, and boom, look at that. All right, so now we've created all these other variables, and now let's say I wanted to plot it again, right? So I'm going to clear filter data. This is just a working variable that we don't really need. So now it's separated by variables. So now let's say I want to plot that same anterior posterior direction. So I want to do another figure, right? And this just makes a new figure for you. And now I want to plot. Now I can go FP1 underscore FY. I believe that's what we were just looking at before. And this is it, right? So now what you'll see is, remember we were looking up here before and we saw like a lot of things happening, right? It basically smoothed it out. So now the curve looks a little bit more like you would expect for an anterior posterior ground reaction force curve. Again, it's sort of flipped though. It's the opposite direction. It looks like it has a positive force and then a negative force, but the way we want to think about it is acting on the person. So initially, when you put your foot under the ground, the force in the anterior posterior direction should be backwards. You have that braking force. So what we're going to need to do next is sort of flip these around to make it so they are in the person's reference frame. So again, we sort of looked at the orientation of these variables. So we did that by plotting, right? So now, again, we plotted, here is where we plotted the sort of analog unfiltered data. Okay. We set up some parameters, filtered the data. Now we're checking the sort of orientation. We can also plot FPFZ, right? So what does the Z forces look like? Again, flipped, right? So we want to think about it the other way. So how am I going to do that? I'm just going to make a new variable. I'm going to say FP1 underscore FZ, FP1 underscore FZ flip equal that. I'm just going to say it's negative. Okay. So just like that, now if I were to figure plot, I'm just going to copy and paste this. Okay. Right. So I need to execute this though, right? Because I need to make the new variable. So if you look over here in the workspace, it's not here right now. So I need to execute it. Now you can see there's FP1 FC flip. Let's plot it. Now that looks like how we would expect it, right? Now we can see the characteristic double hump. This is 1 foot on force plate 1, the left foot on the ground. Then there's no force, right? Because their foot's swinging. Then the left foot's on the ground again. It's swinging, left foot on the ground again, swinging. All right. So I guess I kind of just did plot the vertical ground reaction force, but what if we wanted to actually plot, what if I wanted to plot both the ground reaction forces, right? So not just the left foot, but we have two force plates here, and when we're walking, you're walking with the left foot on one and the right foot on the other. So let's plot them both. Let's do another figure here, a new figure. And let's say we want to plot FE1 underscore FZ flip. Okay. That's what we just plotted before. But I want to plot more than one thing on there. So I'm going to use this code called hold on. And then I want to plot negative FP2 FZ. So this is doing the same thing. I'm just doing it in line. I'm not making a new variable right now. I'm just saying it's negative, which honestly is kind of a bad way to code it. It's not a good habit to get into, so I'm going to do it the right way. So I'm going to go back up here, FP2, and this is FP2. Right? So I'm going to make every variable I flip, I'm going to call it this flip variable. Okay, so now I have my FP1 and FP2 flips. I don't have to mess with this negative sign because that'll mess me up later, I'm sure. I can say hold on, and then the title. So what is this? What are we actually plotting? If I go title, and this is going to just be the vertical ground reaction forces. On our axes, so our X label, our X axis is just, right now, it's samples. 1200 hertz, because that's how fast we are collecting it, just so you know it's sort of in time. Y label, newtons. So that's what our force plate measures. It measures it in newtons. And then for our legend, right, the first thing we were plotting was the left belt, and then the right belt. Left and right force plate. All right. That should be good. So I make the new figure. I'm going to plot force plate 1 and force plate 2. And here we go. So does this make sense? Does this data seem legit? So on the left belt, right, we have left foot strike, the double hump, and then 0 when the foot's in the air, and then left again. And while that's in the air on the right belt, we have the right foot hitting, right? The right foot hits, double hump for the right foot, double hump for the right foot. Okay, and at some points there's 0 force, and at other points there's 2 feet in contact with the ground, right? So these points between right here and here, where there's force on the left and right belt at the same time, that's your double support phase. Okay, so now you're starting to see what the data is going to look like. So how would we find the initial contact and toe off for some steps, right? Because we need to separate this. So some of the things I'm asking you for on the CDP are calculating for individual steps. So how are we going to start to segment out individual steps? What's sort of like an easy way that we can think about doing that? If we pull up that graph again, right, you can sort of see it looks a little confusing when we have both forces on there, but we're only looking at left foot for this, right? So if we're only looking at left foot, maybe we should just plot force plate 1. So I'm going to remove this now. I'm going to hide it. Okay. So now let's make a new figure. Again, it's going to show right belt, but it's not going to be the right belt. It's only left belt. Okay. So how can we look at this signal here and start to be like, okay, well, obviously the initial contact's right here, right? Like I can point to it. There's one heel strike, and there's toe off. And here's the next left heel strike, and then toe off, and then heel strike, and then toe off. So I could click on these points if I wanted to, but I'd have to get pretty close, right? And then with the noise, right, are we sure that this is where the foot hit the ground, or was it here, right? Usually you'll use some sort of threshold to say, well, once force gets above 20 newtons or 25 newtons or 50 newtons, that's when we're sure the foot's in contact with the ground. So it's not just noise, right? The filtering helps that, but sometimes when you have noise spikes in the data, you might have some weird spike here that would confuse you, right? So we filtered out some of the data, but still it's probably good to use some threshold. All right, so how do we want to do it? Well, I think we can probably make it easy by just saying we're going to click a few points. So I'm going to use my cursor. I'm going to click and say this is a left step, this is a left step, this is a left step. And then what I want to do is I'm going to let MATLAB sort of go forward and backwards in time from that point and say, well, this is the time point when it got less than 50 moving to the left in time or backwards in time, and this is forward in time from the point where I clicked where it got less than 50. And if we sort of box that in, then we can use that as our footsteps. All right. And so how are we going to do this? Well, I think we need to probably set some threshold, right? So let's set our threshold to equal 50. Okay, so 50, and this is in newtons. Okay. Oops. Okay. So what I'm going to do now is I'm going to use something called menu. So if we have this plot up, where'd plot go? Actually, I'm going to close all these other figures because we got a lot of stuff open right now. And then I'm just going to plot this one. Okay, so here it is. So some of the code that you can use, so if I want to click, like if I click in the middle, right? If I click on this point and I say, all right, I want to find that time point in X, whatever this X value is of where I click, and then I'm going to move left and I'm going to move right, and I'm going to find basically when it just barely crosses 50, and then that's going to be an individual step. So what I'm going to do is go here, and there's a code calledginput, right? This is a MATLAB function called ginput, and it gives you two values. So it gives you the X and the Y value. Ginput. And it gives you those values for however many clicks you want. So let's say 3, because we're going to find 3 foot strikes. So if I set, again, we need to make sure we're evaluating all of our things. So there's our threshold for now. I need to find these 3. So if I go like this, ginput, what happened? Well, it says it's busy. Well, what's it busy doing? Well, if I come over here, oh, look, I got this cursor now. Okay. So now if I pick 3 foot strikes, I'm going to pick in the middle of 3. So there's left 1, left 2, click, left 3, click. And now if I look at, well, what is my LX value? Get a little more space. So it's 1 times 10 to the 3 multiplied by 1.3, 2.5, and 3.9. So that's basically 1,300-ish, 2,500-ish, 3,900-ish. So those are my X values right there. Okay. But this is also kind of weird. Like if let's click on LX here. How precise did it give me a value? So 1 point times 10 to the 3. 1, 3, 1, 2, 3. So it gave me 1,320.3. So that's some pretty legit accuracy. But the problem is we don't even have point samples, right? We just have one value at each of these points, right? So it let me click in between sort of samples, which is a little odd. I mean, I get it if you're just clicking around, but here we want to know what that number is. What's the value at sample 1,320? There is no sample 1,320.3, right? So let's go back to the code real quick. And now what I'm going to do is I'm going to round them. So I'm going to use MATLAB has a rounding function. So let's just say that our sample, we want to see what's the individual samples for these left foots. I'm just going to round LX. So let's see what that does. If I round LX, oh, there we go. So that just gave me the closest point to where I picked. Okay, so now we have a starting point. So let's just look at the first one. So if I want to find a time, right, whenever this value, right, because if I can evaluate that value LX. So we have 3 different clicks, right? So let's say I want to look at, well, what is force in the Z? So here's our force plate 1 FC flip value, right? So this is what we're plotting. What is my force value at frame 1320? I hit F9. It's 549. I can go back to my thing here. Where did I click? Okay, I clicked pretty much right in the middle there. So that's what the force was at this time point. Okay. So I want to know, well, at what frame, right? At what frame, if I start here, if I start moving backwards in time, at what frame do I get less than 50? Or what should be right around here? Okay. So what I can do is write what's called a while loop. So I can say while FP1 FZ flip is greater than threshold, right? So whenever that is greater than the threshold, what I want to do is find the time frame, and we'll call this ground contact. So ground contact is going to equal ground contact minus 1. So I'm going to keep moving back. And the first thing I need to do is I need to start. I'm going to initially say my ground contact equals sample L1, right? Sample L1. So we're going to start with that 1320. I thought I did this. Sample L. Sample L1. Okay, there we go. All right, so ground contact, we're going to say, all right, we're going to have to find it, but we're going to start right in the middle. So we're going to start with it equal to 1320. And then while this is greater than the threshold, I want to go back in time. Okay, so I'm just going to go back one frame and check it again. And I'm going to go back one frame and check it again. So if I put a little breakpoint here, I'm going to save it so I can do that, right? So we're starting with 1320. I'm going to run this while loop. So it stopped right here, okay? I'm going to, where's step? Huh. Where'd it go? Did it run the whole thing? So what's my GC? 1320. What am I doing wrong here? I think it was stopping, but I'm not sure why. Let's see what happens again. Oh, I didn't even evaluate it. Of course. What is, yeah, while this? What is this? That's a ton of things here. This needs to be while. I'm looking at an individual time point here. Duh. GC. So when we evaluate, right? So here we go. So at that point, it's 549. So while this is greater than our threshold of 50, okay, it's going to do this now. Now it should work. Okay, I'm going to run the while loop. You can see it. I didn't put a semicolon here, so it basically went every single frame. So it went one by one, every single step, back, until the point when it got less than 50 newtons or whatever our threshold was. And that time point was frame 894. So now if I want to say, well, what was this at frame 894? It should be less than 50. 46, okay? So this time point, while I'm running that while loop, right? So now I can say that our actual ground contact, right, for the left foot equals whatever GC is. So now for that first step, we found what the initial contact time was. But that only worked for one, right? That was one of our clicks. We needed to get averages of 3 different foot strikes. I clicked here, I clicked here, I clicked here. So how do I take this and now extrapolate it to do it 3 times? Well, to do that, what you can do is run a for loop. So here we can say for I, which is our changing variable, equals 1 to 3, right? So the first time we're going to let I equal 1. Our ground contact is going to be sample L of I. So the first time it runs through, I is going to equal 1. It's going to look at our first click. Then we're going to say, okay, while FP1Z of GC is greater than the threshold, we're going to go back. And then we're just going to save this as GCI. And so again, it's going to do the same while loop, but it's going to do that 3 times for I equals 1, I equals 2, I equals 3. Again, because our samp L, right, our samples are these 3 values. So it's going to do it 3 times, and it's going to save it to ground contact left. And it's going to be the same column vector. All right, and there we go. So there's our column vector of ground contact left. The first one is 894. The second one was 2,189. And the third ground contact was 3,515. And those are in sample numbers, right? If I go back here, does that answer make sense? 894. That is right around 872. And where does it cross 50? 894. Okay, that looks like it makes sense. What about over here? Is that around 2,000? Yeah, that looks good. And what about here? That looks good. Okay, so automatically, right, we just click in the middle of these. Now MATLAB can find the ground contact times for each of those. So now what we need to do here, we found the initial contact or ground contact. Now we need to do a similar thing, but find toe off, right? So now we need to do the similar thing, but instead of finding this point in the curve, I want to find this point. And I'm going to let you do that one on your own, right? So you're just going to adapt this code. Instead of finding ground contact, what you're going to find is toe off, and you can call that TO. That always makes sense. Okay, so now we're in there. We're starting to separate these values. And once we separate them, we can now separate the total ground reaction force into separate steps. So you're going to use these time points above, and you can say, well, I want to find, let's just set one right now. So let's say toe off is about 1733. We should be more precise than this, but for now, I'm just going to say TO1 is 1733. I'm going to say it right here. TO equals 17. What does GC look like? Let's just guesses on all 3. 1733, 3018, 4346. Is this going to match this? Is it going to look the same? All right, look the same. Okay. So now, if I want to plot step 1, right, I can say, well, let's plot. And again, let's do the vertical, FP1, FZ, flip. I want to plot from ground contact time of left 1 to toe off of the left foot 1. So this is 894. This is 1733. I want to plot between these two. So it's basically taking this whole signal and plotting those values. And maybe I made a mistake. What did I do? Wait, what is this? 1733? Oh, I didn't even plot it. I'm losing my mind, people. I'm losing my mind. There we go. Boom. Right? So that looks like a representative ground reaction force curve. You got forces on the y, samples, again, starting at 0 now, 0 to 840 samples, right? So if we wanted to figure out how much time this was, I could take these, right? Each sample here is 1/1200th of a second. So I can multiply this as our entire stance time is from 0 to 840, right? So if I wanted to figure out what is my stance time, I could just take TOL of 1 minus GCL of 1, right? So that's just the difference between toe off and ground contact. So 839 frames divided by 1200. Again, 0.7 seconds is how long the foot was in contact with the ground during walking. And this was loaded walking. Okay. So now we plotted it. It looks correct. The time seems right in my head. Again, here we start to get in some other details. So one gate cycle, so that's stance phase, right? But one actual gate cycle is from left initial contact to the next left initial contact. So a gate cycle is actually from this time point here to this time point here, right? That's the whole gate cycle. Left contact to left contact, where this is stance phase, and then for this is swing phase. Okay, so I think I give you some tips now about things you should probably start to do, right? How can you plot this not with samples, but with seconds on the x-axis? Hopefully this will help you a little bit with that. If we're trying to normalize and manipulate our ground reaction forces, well, what is the subject's body mass and what's the total mass? Remember this trial here, we can look at trial name. Let's open that back up. Trial name, right? This is Team 99, GF, male, 33, 88 kilograms. That's body mass. Walking, loaded, right? So this is also with the weight of a rucksack on. So you might want to manipulate each of your file names to automatically tell if it's loaded or unloaded. Because if you need to normalize the body mass, well, you know that's 88 from, again, the trial name, 88 kilograms. But how do you get mass to weight, right? You got to multiply by 9.81. But what about the total mass? If this is loaded, then we also need to add in what is the weight of the rucksack, right? And multiply that, or the mass of the rucksack, and multiply that by 9.81. Okay, so here's some other tips, like, so finding the peak ground reaction force. How do you do that? Well, you might want to find a MATLAB function that can give you the peak, right? It shouldn't be terribly hard. If you have something that looks like this, like, well, where's the peak? Well, it's right here. Duh. It's not that hard for me to figure it out, right? But do I really want to, like, come into every single file, right? We have to do this for 3 steps, right? So it's 3 steps per person per trial. So think about how that really adds up, right? I need to do it for 3 steps here, and then 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 3 steps here, and 3 steps here, and 3 steps here, and 3 steps here. So you have to do it basically 10 times 4 times 3 times to figure out what the peak is. Do you really want to just plot it and like start to bring out the cursor, and then you're like clicking, and is this the peak or is this the peak, right? It's so much easier to let MATLAB do the work for you, right? And once you have it segmented into something like this, right? Like, it's not hard. You know it's here. How can MATLAB tell you what that point is? Well, right, if we know, here's the values we want to look for that first foot strike, right? These are all the values we want to look at, right? MATLAB just spit them out for you. MATLAB should be able to pretty easily tell you what the max is of that, right? Well, how do you find out? How do I find out what the peak is? Well, I could like basically go to Google and be like, Google. This is what I was doing right before this. Remember when I said the MATLAB live script wasn't working, it wasn't plotting? Well, MATLAB live script not showing figures. And there's like a whole bunch of stuff. Sometimes it's easy, sometimes it's hard. Wasn't really worth it for this. But now, if I want to say MATLAB find the max or find a peak, find peaks. Peak. So there's a function called find peaks, which returns a vector with the local maxima peaks of the input. Well, do I want local maxima? I can watch a video on it. Let's see, peak analysis. Well, look at that. Important area signal processing, and this will find all those peaks, but I don't want the peaks. What if I just want the max? Is there another way to get it just the max? What about just finding like the max? Oh, I don't know where I clicked, but that was a weird spot. Let me go back to Google. Not Gmail. Let's just go to Google. Okay. MATLAB max. MATLAB max function. Well, would you look at that? There's a function just called max. Then I come here, max of that step. What's it going to be? Boom. 1.385 times 10 to the 3. If I go back to the plot that I actually want, does that make sense? Is this about 1. Oh, there it is, 1.385. There's the peak. We can even probably zoom in on it if we wanted, just to see what's happening. Get a little more resolution, but that's right? So now you've written some code. You have an algorithm to find the peak, and it worked, right? It found the right thing. Now you can iterate this, right, using for loops to go through all of these one by one and to do everything you need, right? Like identify the vertical ground reaction force at 3% and 12% of stance. That's for average vertical loading rate. So how are you going to find a way to figure out what 3% of stance is? We have that figure, right? We have this figure. Where is 3% of this figure? Well, you'll have to look at, well, how long is this step phase in particular? 840 frames. What's 3% of 840, right? Make sure that lines up with an actual number. You might need to do another rounding because, again, we don't have like frame 17.5 or 27.2. There's only frame 26, 27, 28. And again, it's enough resolution because we're capturing 1,200 frames a second, but still, you need to make sure MATLAB's doing the right thing. All right, so that's how you look at finding your vertical ground reaction forces, finding impulse, right? So how do you find impulse? What is impulse? Well, that's area under the force time curve. So how would you find the area under a curve if you were doing it by hand? You might remember like doing this in math class back in the day, all right? If you don't have a function, you just have some experimental data. Well, how do you find the area under the curve? Maybe you approximate it with squares or rectangles or trapezoids, right? Does MATLAB have a function to do that for you? Here's a hint. Okay. Again, you need to plot each step with the specific features. Go back, look at the data, or look at the assignment that I gave out. It has very specifics about plotting red triangles and red squares and green lines, right? And that's one to get you some practice with MATLAB, but it's also to help you easily see the points that you're calculating. Hopefully you can look at that plot, and I can look at that plot, and I can know right away whether you did it right or wrong. If it's telling me that AVLR, right, is 2 body weights per second, and then I go to this figure, right, and it's plotting like some point here and some point here for your AVLR and like drawing a line over here, when I know it should be from 3 to 12% right here, right, then right away I know it's wrong. And that's the real reason you're doing this. You're visualizing your data, so when you're writing code, you can find your mistakes, because there's always going to be mistakes, right? That's why going step by step through this, checking back to these figures, making sure it makes sense. Does it line up with what you should? Because once you get this to work for one person, right? Once you get this to work on one walking or one walking and running, then you can run through it and it'll calculate it all for you. Lastly, here's some help that I've used before to help write some of these things to an Excel spreadsheet. So there's a function called XLSWrite, which basically, given the name of your Excel file, it'll write the individual subject name or the weight or male or female into specific cells. So once you have your code that works, just have it write a whole, for every one of these trials, right? It can just write the 3 lines for each of the steps in a row, one after the next. And then you end up with one big Excel spreadsheet with all of the data that you actually want. So it's not every piece of data, right? Because we get tons of stuff here, but everything that you want to calculate, everything that you need to test your hypotheses. All right, I think that's probably enough for the day. It seems like I've been talking for a while. And really you just need to get in here and mess around a little bit. So again, I posted the shell. I'll post the shell. You have this video so you can copy some of the things I've done, especially here, right? A little help with some while and for loops. If you're struggling, let me know. We can set up some AI. But otherwise, I think that's about it. I'm going to stop sharing. While you're in full screen mode. Okay, I don't know what that means. All right. Hopefully this was helpful. Again, don't forget to put in your attendance data and let me know if you need some help. And stop recording.